Hi, we're going to continue on with our bonding unit, and we're going to start drawing Lewis structures. In the last video, we drew Lewis structures for diatomic molecules, but now we're going to draw Lewis structures when we have two different elements. Okay, so here we go. We've got hydrochloric acid. And so the first thing you do is you draw the Lewis dot structure for the elements involved. So for HCl, hydrogen has 1 valence electron, and chlorine has 7. Now again, these are both nonmetals, and so the type of bonding that's going to be used is going to be covalent bonding, where the electrons are shared. And so hydrogen would like to have 2 electrons in its outermost shell, chlorine would like to have 7, so they're going to share electrons. So we can write it like this, and the shared electrons are represented by that dashed line. So that is our covalent bond, and it is 2 electrons that are shared. And so hydrogen is like, hey, I have my 2 electrons, and chlorine has the octet, or the 8 electrons that it would like to have for stability. Okay, water. We have 2 hydrogens and 1 oxygen. I'm going to just start by drawing oxygen here. It has 6 valence electrons. Then I'm going to draw my 2 hydrogens, and they each have 1 valence electron. And as you can see here, we are going to be sharing these electrons and these electrons to make that covalent bond for water. And so the Lewis structure would look something like this. In a later unit, we're going to learn how we know that this is bent the way that I have drawn it. Okay, so hydrogen has its 2 electrons, this hydrogen has its 2 electrons, and the oxygen has an octet. All right, carbon tetrachloride. Again, all nonmetals, so this is definitely covalent bonding. And carbon has 4 valence electrons. And then we have 4 chlorines, each with 7 valence electrons. Takes a while to draw these valence electrons in this Lewis dot structure. And what you're probably already have figured out is that this structure is going to have 4 covalent bonds, and that's exactly right. So here's one, here's another. Goodness, I think I forgot. There we go. Here's another, and here's another. So chlorine with its 7 valence electrons is going to share 1 of them with carbon, and so we wind up with carbon tetrachloride looking like this. And these have all been single covalent bonds. And drawing the non-bonding pairs can be time-consuming. So again, just some more practice with using valence electrons to form covalent bonds between nonmetals. Now this is a term we've been using pretty much all year, electronegativity. It's the ability of an atom to attract electrons to itself when the electrons are shared in a chemical bond. So now this whole definition makes perfect sense to us. The shared chemical bond, which is our covalent bond. We remember that the most electronegative atom is fluorine, and so on the periodic table, as you go from left to right, electronegativity will increase. And when we go from bottom to top, the electronegativity will also increase. All right, now let's go ahead and learn about polar and non-polar covalent bonds. Now, not all electrons are shared equally because of that electronegativity. Now, if the electrons are shared equally, that's called a non-polar covalent bond. There's no separation of charge. And examples of this would have been for our diatomic molecules. So here we have chlorine with chlorine, and you know, which chlorine is more electronegative? It has the same electronegativity. And so the electrons in that shared bond, they are shared equally. So we are going to now classify that as a non-polar covalent bond. But something like the HCl, all right, these electrons in this covalent bond, chlorine is pulling on them more tightly. Remember, chlorine is more electronegative. One way that we can show that is we can draw an arrow toward the chlorine, showing it's pulling on those electrons more tightly. And then that gives the hydrogen a slightly positive charge. That's called a dipole moment, when we have a separation of charge due to electronegativity differences. And there's actually values for these. The way that we have been showing it in class, we have talked about the chlorine having a partial negative charge. That's what that Greek letter delta means. So the electrons are spending more time around that chloride molecule, giving it a slightly negative charge, and then the hydrogen has a slightly positive charge. So this is where the electrons are not shared equally, and that is called a polar covalent bond. So electrons are not shared equally. And so we wind up having a separation of charge. So a polar molecule, separation of charge. In that last slide, we also drew water, and the oxygen in the water is more electronegative than the hydrogen. So that's what gives it its slightly negative charge. And then the hydrogen has the slightly positive charge. These covalent bonds are also polar because the electrons are not shared equally. And then in our carbon tetrachloride molecule, these shared electrons are not shared equally. The chlorine is tugging on them a little more aggressively than the carbon. Chlorine is more electronegative than carbon. So we have all these chlorines have a slightly negative charge, and the carbon has a slightly positive charge. So again, these single bonds are polar covalent bonds. So polar covalent bonds are when electrons are not shared equally, and that's due to electronegativity differences. All right, we are going to start drawing Lewis structures in class, and we have this little set of rules. So far, we've been able to kind of figure out how to draw Lewis structures just based on knowing that hydrogen wants 2 and all the other elements that we've been, or all the other atoms that we've been dealing with want 8. But sometimes it gets a little bit tricky. And so there's a set of rules for drawing Lewis structures. And so here they are. I'm not going to read them to you, but you're going to want to refer back to this as you learn how to draw Lewis structures. And I'll show you just an example, and then we're going to work a lot in class with this. Let's draw a Lewis structure for in this case, let's do carbon dioxide. Okay, rule number 1, you count the number of valence electrons that you have. And so we have carbon, and how many valence electrons does carbon have? It has 4. And oxygen, how many valence electrons does oxygen have? It has 6, but we have 2 oxygens. So we have a total of 16 electrons that we have to work with. Okay, now I make another column of how many valence electrons would we want. Every element wants 8 with the exception of hydrogen, who wants 2. So carbon wants 8 and oxygen wants 8, and we have 2 of them. So all in all, we want 24 electrons. Well, we don't have what we want, and so the difference between this, and that is going to be 8 electrons, that is going to be the number of electrons that are shared, and the electrons are shared in pairs. So if we divide that by 2, we find out we're going to have 4 shared pairs of electrons. Now the electronegative elements are on the outside of the molecule. So we're going to put carbon in the middle, and we're going to put oxygen, because it's more electronegative, on the outside. So now you just draw your skeleton, 1 carbon and 2 oxygens. We need 4 shared pairs. Well, there's 1, there's 2. For 4 shared pairs, we're going to come in and draw double bonds. We now have 4 shared pairs. Carbon, remembering that each of those bonds is 2 electrons, carbon has an octet right now, 2, 4, 6, 8. This oxygen has 4 electrons in its outer shell, 2, 4. So we're going to finish up with lone electron pairs to give it its octet, 2, 4, 6, 8. And same for this. When you're all done drawing your Lewis structure, make sure that everything has the 8 valence electrons, or 2 if it were hydrogen. And now we're going to count these up and make sure that you have represented what you have. 2, 4, 6, 8, 10, 12, 14, 16. Yes, we have 16 in the Lewis structure that we've drawn. All right, in class we're going to practice drawing things that have charges. We're going to learn something about resonance structures. So anyway, we'll see you in class.